Okay, folks, it is that time of the day. I wanted to just begin with a quick reminder. The material that I am covering right at this moment, or what we'll be covering today, I should say, consists of some of the most missed questions on exams. The reason is that when you get into the names of compounds, it's either right or it is wrong. There is no middle ground. There is no partial credit. When you get into the formulas of compounds, it is either right or it is wrong. There is no partial credit that can be given. Now, I'm saying this not to frighten people, but to put you on your guard and hopefully make you realize that you cannot wait to start studying for this exam. This exam, you really and truly need to start studying in bits and pieces all along. And I'm talking more than just the active homework. The active homework is okay, but you really need to put in more on this particular one, because it is going to be that the majority of the material on this exam is right or it is wrong. So I'm just trying, again, to put you on your guard, not to scare anybody, but to hopefully make you realize that you gotta do some time on this one. More so than on any others. Now, is it topics that you most likely have heard about in previous chemistry classes? Yes. But it's still something you've got to put in the time and effort for. So, what we will be doing today in lecture and in lab, is we are going to be focusing on naming compounds and writing the formulas of compounds. In class this morning, we're going to focus on ionic compounds. And in lab this afternoon, we'll focus on covalent molecules. We'll focus on acids. And then we'll get into some calculations associated with these compounds. So that is the plan for today as a whole. Any questions? Now I pulled up this table because again, this table, the way it is shown, is extremely important in figuring out what to do when. What did the blue indicate on this table? Yes. These are metals that always form the same charge. And that's important because if it's a metal that always forms the same charge, then when we go to name the compound, we're just going to list the name of the element. Now, does anybody know what charge group 1 metals form? +1. How about group 2 metals? +2. What about silver? 1. Cadmium and zinc? Aluminum, gallium, and indium. Okay. Now, why did I highlight all the rest of the metals in red? Yes. Those are metals that can have different charges. So what do I need to include when I start writing the name of those ions? Roman numerals. And we'll go over the Roman numerals a little bit more here soon. Now, folks, these Roman numerals, if I give you the name, of course, I'm going to give you the Roman numeral. So I will be telling you the charge. But if I give you the formula and I'm asking you for the name, you'll be like, well, how am I supposed to figure out what charge these ions have? And the answer to how do I figure it out comes from the anions. Because all of the anions always have the same charge. Their charges never change. And because the anions' charges never change, you can determine what the charge on the metal is. So I highlighted the green because these are your nonmetals and metalloids that form anions. What charge does a group 15 nonmetal or metalloid form as an anion? -3, group 16, -2, and group 17, -1. The rest of it is purple. Why? What is the purple about? On this one. If you have compounds that consist of nothing but the purple elements, it means they're covalent molecules and they don't have charges as a covalent molecule. So these in green and purple,
It's green if it's in an ionic compound because it'll have a charge. But it's purple if it's in a covalent molecule because it won't have a charge. And then you had your polyatomic ions, which I tried to give you some trends to help you memorize, to cut down on the amount of memory work. And those are going to be used in ionic compounds, which is what we will be talking about this morning. So just as a reminder about ionic compounds, this is again in Monday, Tuesday's notes. Ionic compounds contain an ionic bond. An ionic bond is nothing more than basically a magnetic attraction between a cation and an anion. And the cation is going to be either a metal or it can be ammonium. But the cation results from the loss of electrons. Those electrons are transferred to the anion, which is the nonmetals that gain those electrons. And basically, an anion is just a negatively charged ion. So the majority of your polyatomic ions are anions. And then you have those metalloids and metals in group 15 through 17 that are anions. When we write ionic compounds, they're always going to have a formula that has the cation and anion in the smallest whole number ratio possible. So let's talk about writing ionic compounds. First of all, one thing to note is the cation is always listed first. It doesn't matter whether we're talking about the formula or whether we're talking about the name. The cation will always be listed first. Now, let's talk about developing the formula. The easiest way to develop the formula is to cross, drop, and simplify. We will cross the magnitude of the charge and drop it on the opposing ion. Then we simplify so that the formula is in the smallest whole number ratio possible. So let's just look at a couple of examples. We'll be actually doing lots of examples. But we'll start with a couple, and then I want to do the discussion on the naming and then go from there. So now I want to make one more note about the formula. And this specifically deals with polyatomic ions. If more than one polyatomic ion is needed to make the ionic compound charge neutral, then the polyatomic ion is placed in parentheses with the quantity required as a subscript to the right of the parentheses. So we're going to cross drop and simplify, but if as we are dropping the magnitude onto a polyatomic, if you need more than one of them, then you're going to need to put the polyatomic in parentheses in creating the formula. You don't have to do it if there's only one of them. Okay. So examples. Let's take aluminum. What charge does aluminum have? I heard it, 3+. And let's combine aluminum with sulfur. And what charge does the sulfur atom have? 2-. You may, one thing I will say, you will see me write charges where I put the magnitude prior to the sign. And the reason I put the magnitude prior to the sign on a charge is so that I can differentiate a charge from an oxidation state, which we'll talk about later in the semester. So that is why we write them in this particular order, is so that we can differentiate what is an ion charge from what is an oxidation state. Okay, we have aluminum and we have sulfur. We're going to take and we're going to cross the aluminum's charge magnitude or the aluminum's magnitude and drop it onto the sulfur. We are going to take the sulfur's magnitude and drop it onto the aluminum. So we wind up with Al 2 S3. And that is the formula of a compound that contains aluminum ion and sulfide ion. Again, we only drop the magnitude. We don't drop the sign of the charge. Let's look at another one. Let's look at chromium 6+. And we're going to mix that with phosphorus. And what is phosphorus's charge? 3 negative because it's in group 15. We are going to cross, meaning we're going to, whoops. We're going to take the 6 from the chromium and drop it onto the phosphorus. We're going to take the charge of the phosphorus and drop it onto the chromium. So we will get chromium 3, P6. But this is where that other stage comes in. We got to simplify. Both of these numbers are divisible by 3. So we have to do so. So the actual formula is chromium CrP2. We simplify ionic compound formulas. As we'll discuss in lab, we do not simplify covalent. We only simplify ionic. Yes. You always get a periodic table. So yes, you will. Highlighters are definitely going to be beneficial this test because you can do a quick highlight of what needs to be where. Yes, I'm very color coded if you can't tell. I think it helps. Okay, so let's look at another one. Let's combine calcium. What charge does calcium have? +2. With hydroxide. What is the formula for hydroxide? It is one of the few polyatomic ions that end in IDE. OH minus, which means there's a -1 there. So we're going to take the calcium, we're going to drop its charge on the hydroxide. We're going to take the hydroxide's magnitude and drop it onto the calcium. So we get 1 calcium, but we need 2 hydroxides. Because we need more than 1, what do we have to do? I need that hydroxide in parentheses with the quantity needed as a subscript to the right. Questions? Yes.
If it's polyatomic, would you put the magnitude after the charge?
It doesn't matter. When it's a 1, I just put up a 1 so that I actually don't usually even do this step anymore. But as you're learning, it's easier to remember this step. So if it's a 1, I just throw a 1 somewhere so that you can see it. But no, if you look back at all the polyatomics, they're typically written in a magnitude, then sign, order, except for the 1s. Other questions? Yes.
Still don't quite understand why in the parentheses.
The polyatomic ion itself is OH. And so what you're saying is, I have 2 of these entire things by putting it in parentheses. You're saying you have 2 of the entire thing. Did that answer your question? Yeah. Okay. Other questions? Okay, so this is straight, this is if you're given the ions, but let's talk about going from names to formulas. We're only going to add 1 step, folks. to what we've been doing. If you're going to go from name to formula, the first thing you're going to do is translate the name into the appropriate ions. Then you'll cross drop simplify. So we're only adding one new step, and that's the translation. However, that step is huge. So before I do any examples, I want to discuss that step. First of all, the first thing listed will be the cation. And you can write whatever you need to write of what I say, but I am not gonna be writing it down. The first thing you read is going to be the cation. Now, the cation is going to be shown in one of two ways. You will either be given just the name of the metal, and if I'm given just the name of the metal, what does it mean? Not quite. Huh? Not quite. If I'm given just the name of the metal, what does it mean? I think I saw it. I think I saw it now, but not said.
The charge stays the same.
The charge stays the same. In other words, folks, if I give you the name of the metal, it's going to be, and that's all you see. It's going to have to be either group 1, which is a +1, group 2, which is a +2. Silver, which is a +1. Zinc cadmium, which is +2, or aluminum gallium, which is +3. So if I give you the name of the metal, it's one of the elements whose charges is always constant. The second option for that cation is I'm going to give you the metal and I'm going to give you the Roman numeral. By giving you the Roman numeral, what am I telling you? The charge. I am telling you what the charge has to be. So just a quick reminder of Roman numerals. I is 1. I is 2. I is 3. IV is 4. V is 5. VI is 6. VII is 7. And I won't go past 7. I think there's one element out there that can go up to an 8. But I think it's only one element. So if I give you the Roman numeral, I am telling you what the charge is. So cations are one of two things. They're either going to be just the metal, which means it's got to be a constant charge all the time, or it's going to have the Roman numeral with the metal's name, which means I'm telling you the charge on that metal. Now, the anion is the more complicated piece. Because you gotta recognize suffixes. Anion is the more complicated piece because you gotta recognize the suffix and understand what it means. If I give you a suffix of IDE, what does it mean? It means that it is an anion of an element.
So the anions. If I give you the suffix IDE, it means that it is an anion of an element. There are 3 exceptions to that I could give you. The 3 exceptions are hydroxide. Let me actually write word except. Hydroxide is the polyatomic ion OH minus. Cyanide. Cyanide is the polyatomic ion CN minus. And peroxide. Peroxide is the polyatomic O subscript 2 minus. But otherwise, if you see an IDE, it means that it is an anion of an element. If you see 8, or if you see ite, it means that it is a polyatomic anion. So it is very important to recognize the suffix. The suffix tells you what type of anion you are working with. Questions? So let's look at a few examples. Cation's always listed first. This cation is just the name of a metal. So what does it mean about the metal? Constant charge. What is its charge? Sodium's charge. +1, why? Because it's in group 1. So sodium is a +1. Normally I just write it as Na+, but since I'm needing to cross drop and simplify, I'll throw the 1 in there just so I have it. Sulfate. The ending ATE is telling me something. What is it telling me? That it's a polyatomic ion. It's the polyatomic ion SO4 2 minus. Now, we are going to cross and drop the magnitudes of the charges onto our individual elements. So on sodium, I'm going to drop a 2. On sulfate, I am going to drop a 1, and because I'm only dropping one of them, parentheses are not required. So the formula for sodium sulfate is simply NaSO4. I mean, Na2SO4. This formula literally means that there are 2 sodiums, there is 1 sulfur, and there are 4 oxygens. Let's look at another example. Let's look at ruthenium-3 acetate. What am I telling you if I'm giving you the Roman numeral? Whose charge? The metal's charge. So ruthenium's charge is a 3+. What does the ending 8 tell me? It's a polyatomic. This particular polyatomic is C2H3O2 minus, which is a -1 for purposes of cross drop simplify. So I'm going to cross a 3 onto the acetate, and I am going to cross a 1 onto the ruthenium. So I have Ru. Because I am dropping something other than 1 onto a polyatomic, what do I do to the polyatomic? It goes in parentheses with what I dropped as a subscript. Now, folks, with this particular formula, it means that there's 1 ruthenium. And because I have 3 acetates, it means that there's 6 carbons, 9 hydrogens, and 6 oxygens. Again, because I have 3 of this entire unit, that means there had to be 6 carbons, 9 hydrogens, and 6 oxygens. Or in other words, I took the subscript and I multiplied it by each subscript within the parentheses. Let's look at another example. Let's look at silver phosphide. Because I didn't give you a Roman numeral, what does that mean about silver? It's always the same. And what is silver's charge? It's +1. This is in that little stair step that I showed you in the periodic table where it's the first step. There's only 1 element, so it is a +1. Phosphide. What is my ending telling me? That it's a ion of an element. So it's P. And what is phosphorus's charge as an element? -3 because it's in group 15. So we are going to cross and drop and then simplify. So on our silver, we're placing a 3. On our phosphorus, we're placing just a 1. So the formula for silver phosphide is Ag3P. So again, folks, with taking the name of the compound to the formula, this shouldn't be difficult. It shouldn't. But it always is. But it should not be difficult. But in order for it to not be difficult, you do have to recognize the trends. With respect to the cation, if there's no charge showing, it means it's one of the ones that has a constant charge. You just got to know what that charge is. If I give you an element that does not have a constant charge, I got to give you the Roman numeral because I got to tell you what the charge is. So that's the cation trend. With the anion, it's all about the endings. What does it end in? And that will help you to sort through. Now, folks, a lot of this is still memory work. I'm telling you the trend, but you still, if you don't know that group 1's always a +1, you're still going to screw up. If you don't know that group 2's always a +2, you're going to screw up. So you still got that memory work. All the name is doing is helping you to narrow it down a little bit. That's it. We're just narrowing it down. Is it a metal whose charge is constant or not? Is it a polyatomic ion or not? That's all the name can do for you, is narrow it down. But if you don't have that memory working, you're not gonna know where to go. Questions so far? We've done names. Well, we've done the formula of the ion down to the formula. We've done names where we have to add that extra step and translate the name into the ions in order to get to the formula. The next step is we're going to go from the formula to the name. And a lot of these things that I've been trying to, in a sense, feel like I've been preaching at you, is the important stuff here. You also have to know it too. Because the first thing first of all, cations listed first. So the first thing you got to know is, will the metal or the cation need a Roman numeral? That's the first thing we got to know. Will the cation need a Roman numeral? If you answer no, then you name the cation, name the anion, and you are done. But if you answer yes, then the first thing you got to do is determine the Roman numeral. So that you can name the cation, give cation's charge as a Roman numeral, and then name the anion. Now, over the years, I've tried and tried and tried to come up with a formula. And I've come up with one that works. I find it clunky, so I'm going to show it to you. I'm going to write it and I'll use it, but then I'm also going to show you a quicker way because I do find it a bit clunky. But if you need a formula, you would have one that way. So what is the formula? The charge can be determined using 0 is equal to the number of cations times B. B can be any variable. I could have used X. I could have used Z. I could have used Y. I could have used anything. I'm just needing a variable here. Plus, it is the number of anions times the anion charge. B is just is a variable. Like I said, I could use X, Y, Z, M, N, O, U, V. It doesn't matter. I just chose B because it's a little more obvious. So that is getting from the formula to the name. So let's look at an example or two. Let's go with something straightforward. MgCl2. Using the question I have here, will this cation need a Roman numeral? No. Why? Because of what? It has a charge, but it's constantly the same. What is its charge always? It's always a 2+. So it always has the same charge. So since it always has the same charge, I'm going to name the cation. And I'm going to name the anion. What is the ending, the suffix for this anion going to be? I to Y. I think I heard it, because it is an element. So this is chloride. So that is the formula for magnesium chloride. Again, I use the ending IDE because I was talking about the anion of an element. And again, there is no Roman numeral. Because magnesium is in group 2. And therefore, its charge is always a +2. Let's look at another example. Let's look at MnS. Looking back up here, cations listed first. Does the cation need a Roman numeral? Yes. The Roman numeral is required. So this is where I'm gonna go assign things. I have one manganese whose charge I do not know. I have one sulfur. And since it's an anion of an element, what is its charge? 2 minus. So if I'm using my formula, 0 is equal to 1 times B plus 1 times the negative 2. So 0 is equal to B minus 2. So B has to equal a plus 2. So this is manganese 2, because the Roman numeral tells you the charge. Now I just need to name the anion. What is the ending going to be for this element? For this anion? I'd, because of the fact that it is an anion of an element. Let's look at another example. First of all, let's deal with cation. We got to answer this question. Will the cation need a Roman numeral? Yes. So I'm going to assign a B to my gold cation. And what is sulfite SO3's charge? It's a 2 minus. So 0 is equal to 2 times B plus 3 times a minus 2. 0 is equal to 2B minus 6. 2B equals 6. B equals 3. Questions? So my cation is gold 3. Again, Roman numeral needed. Because the charge on gold can vary. is the anion? What ending is it gonna have? ITE. This is sulfite. The ITE tells me that it's a polyatomic. Yes.
Why wouldn't it be A?
Sulfate is SO4 and this is SO3. So you got to know your polyatomics to know whether it's going to be 8 or I. But if you'll recall on Monday, one of the things that I mentioned is when you get to that period 3, that 8 has 4 oxygens. Since this has 1 fewer, it's the I version of it. Questions? So it's not going to be this neat and tidy on an exam. One of my goals is before we move on to naming, before we move on to doing a few calculations today in the labs time frame, I plan to mix it all up because that's how it's going to appear on a test. Is all mixed up. So you've got to learn to ask questions. Which reminds me, I need to print some things off for you. Another thing off for you. Any questions about ionic compounds? Again, ionic compounds contain an ionic bond. An ionic bond is the electrostatic or magnetic attraction between a cation and an anion. Their formula must always be in the smallest whole number ratio possible. That is why we cross, drop, and simplify. If it isn't obvious, you've got to know your metals that always have the same charge and what that charge is. So that's memory work right there. You got to know your elemental anions and what that charge is. That's memory work there. And then you got to know your polyatomic ions. And polyatomic ions, again, their formula is always the same. Their charge is always the same. They never change. And you got to remember, and that's memory work there. So there's lots of memory work in this first piece. And without it, you cannot do some of the stuff we just did. Okay, then we're going to move on to covalent molecules. Covalent molecules, again, have a covalent bond, which arise through the sharing of electrons. Because electrons are shared, the elements in covalent molecules do not have a charge. I'm not gonna say that when we get to, for instance, the acids or some of the other things, I don't include a description of the charge, because the charge is what it is for a reason. The charge on these elements are what they are because of their electron configurations. And there is a relationship between the charge and the number of valence electrons. And so there's a lot of overlap, but what I want you to know is when it forms a covalent molecule, they don't actually have charges. Covalent molecules do not have to be in the smallest whole number ratio possible. So we're going to talk about 4 types of covalent molecules today. I'm going to start with diatomic elements and hydrogen. I may quit after that and pick it up in lab. There are 7 elements that, when found in nature by themselves, come in pairs. I want to emphasize this statement of it's by themselves, because the reason I want to emphasize that is we're going to see that when it forms compounds with a second element, they don't necessarily come in pairs. It's only when they're all by their little lonesome in nature that they come in pairs. The easiest way, there's 2 ways to memorize. Who the 7 are. Method number 1 is to memorize Brinkelhoff. Brinkelhoff. These elements, when found in nature by themselves, always come in a pair of 2. The second way to memorize them is to look at the periodic table. For the number 7 and add hydrogen. We start with nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. There are 7 diatomic elements that form a 7 on the periodic table along with hydrogen. So that's the second way to memorize it. Take your pick. Brinkhoff. You may have another one that you learned from a previous class, but for me, the two that I kept in mind were either Brinkhoff or the fact that they form a nice little 7. And you add hydrogen. If I give you oxygen, in other words, you better give me back O2. If I say bromine as a molecule, you better give me back Br2. Because that is how they come in nature. So, for the formula, the element has the subscript 2. For the name, it's simply the name of the element. So if I say iodine, I am talking I2. If iodine isn't a compound, it's no longer stated as iodine, it's now stated as iodide. But if I say iodine, I'm talking I2. That's all there is to the diatomics, is knowing who they are and realizing that their element name is the same as the formula. Or is that formula with the subscript 2. More memory work. Because you got to know Brinkhoff, or you got to know the 7 plus hydrogen. Now, I will say that I did make a Quizlet of the diatomics. So there's a Quizlet for you of the diatomics to help you out a little bit. Questions? Okay. Well, we're going to get out 8 minutes early, 9 minutes early, because let's face it, we're going to have a long lab going over more naming. And you got a lot of work ahead of you going over all this naming. And I will tell you in lab how to start studying for this naming and formula piece. I would do it after lab. That way I can just include lab stuff into it. I got to go write it.